cover this now, because the next experiment is also very similar to this one, except with a very small change. So this experiment was developed by Craig and Tulving in 1975, and they wanted to see whether what kind of words are actually remembered by people, whether they are deeply processed words, or is there any other criteria in which people actually remember words. So their hypothesis is that words that are deeply processed should be recalled better than those that are less deeply processed. And we already saw from the last experiments that people deeply process things by basically attaching a semantic information to it. So if they had actually if they had actually dealt with, analyzed it semantically, that is deeply with the meaning and all that stuff, then they will be able to, it's basically deeply processing that particular word. So, so what they are saying, the subject simply rate, what the experiment is that subjects will rate words based on structural, phonemic, or semantic aspects. Okay, so structural is how the words are formed. For example, an aeroplane is an arrow means sky, and plane means something that actually goes over the sky. So that is actually a structural part of it. And how many syllables are aeroplane? There are 3 syllables in aeroplane. So that is actually all the structural part of aeroplane. About the phonemic part, so how does that sound exactly? And an aeroplane is basically, as I said, it's an aeroplane. So we're actually attaching an O in the middle of air and plane, something that actually connects it phonemically, like how we are whether it is actually very similar to another word in our language that we know, something like that. So for that is phonemic, and semantic aspects is basically how the word is, or how the word has formed a meaning in your mind. So subjects are asked to rate the words based on this. So if they find the word more, structurally significant, they'll rate that word more as structural. And if they find the word more phonemically significant, they'll rate it as phonemic, and respective in semantics. So, and they actually measure the time to make a decision or recognition of the rated words. So I'll actually give an example, based on this. So this is not the actual data set that they use. This is just an example that I have come up just to see, just to tell you how the rating system works. So if the subjects feel like, this is just one subject's rating system. So if the subject feels like the aeroplane is it has a very cultural structural significance and structural, it has a great structural significance, then he'll rate it more than like 5. This is all like base out of 10. So aeroplane, they'll rate it more than 5. So if the subject has a very strong association of meaning to aeroplane. So he has given a very large semantic rating for it. And similarly for carrot also, they have given a very large semantic rating. And the subject does not think like the word carrot is like structurally significant. So it is all based on what that particular subject thinks. And every answer, every rating that they give is all based on their own life experiences and their own understanding of that word. So so this is how the rating system works, and this is how the subjects are asked to structurally, phonemically, and semantically rate the words. So if we can see, the word violet actually doesn't sound very phonemically significant to the subject, so he has given just a 1 in that, and so on and so forth. We'll see what the significance of these ratings is, in a short time. So the result is that that they observed is that deeper processing takes longer to accomplish. That is to rate the words, to rate the words on a deeper level. People have taken a much longer time. And the recognition of encoded words increases as the function of level to which they are processed. That is, the more that they have processed it in their mind, the more that they are able to recognize those words. So basically, if the subjects were able to give a larger rating for all the three of those categories, then it means that they have actually processed that word a lot in their mind, and that word they were able to remember it much more, remember it much more well. So the significant aspect of this result is that those words that engaging semantics aspects are better recognized than those engaging only phonological or structural aspects. That is, people who have understood the words at a deeper level regarding their meaning, regarding the semantics of it, they were able to, that is, people who rated words as in a semantic rating as a larger scale, they were able to remember those words. So we'll see an example for that. So if you see over here, this subject has actually rated this aeroplane as 8, country as 7, and carrot as 9, and rest of the semantic ratings are like very low for this subject, for all the other words, that is. So what Craig and Tulving is saying is that that particular subject is more likely to actually remember aeroplane, country, and carrot when they are asked to repeat, when they're asked to remember what words were they given to them. They are more likely to give aeroplane, country, and carrot than any other word in this system. They might also have recognized and remembered other words, but they're more like, they will definitely remember aeroplane, country, and carrot because they gave a higher semantic rating for it. That is, the meaning has stricken them in a very deeper level. Okay, so that is Craig and Tulving's. So any doubt on this?
Tarun, the context is when you are suppose given 10 words to remember, after that, which ones will be remembered most? In that,
Yes.
all comes, huh?
Yes.
Okay, got it. Thanks.
No, but at the same time, he also says that it varies with a subject to subject, depending upon how
Yes,
they
yes,
have
it
deeply
definitely
processed.
varies from subject to subject. That is, the ratings definitely vary from subject to subject. But the thing is that if, like, let's say that subject 2 has given a much more semantic rating for the word tour, or subject 2 has given much more semantic rating for the word tap, then they are much more likely, that particular subject is much more likely to have remembered tour and tap.
Got it.
Okay, any other question? Okay, great. So Rogers, Kuiper, and Kirker, they basically wanted to extend this experiment. They didn't do any other change to this experiment other than just one thing. They added a separate category for rating, that is self-reference category. So what the self-reference category is, how much that word actually means to us, as opposed to how much that word's meaning that you have understood, how much that word actually means to you at a personal level. So if that what they have hypothesized is that if the subject is able to have a much more deeper self-reference to that particular word, that is, that word actually means a lot to them, then they are more likely to remember those words than the ones where they are actually giving a higher semantic rating to that. So they were given 40 subjects were given 40 adjectives given to that subjects and rated based on structural, phonemic, semantic, and self-reference aspects. Okay, so as we can see from the experiment itself and from their hypothesis was correct, it was found that the words rated more on self-reference was recalled better, followed by semantic, phonemic, and structural aspects. So, for example, so our new self-rating column has been added to it, or the same set of words, and let's say that this is the rating that a subject has given for this. So here the self-reference rating is high for the words aeroplane, country, and cycle. So aeroplane, country, cycle, and tour, of course. So based on all these words, we can actually form a kind of personality regarding that person. So that person who has actually rated this feels so much about aeroplane, that is, they can deeply relate their self-reference to an aeroplane, a tour, a cycle, and a country. So we can safely say that, this person might be a traveler, or a traveler, or a person who travels a lot might associate himself with these particular words rather than any other word in this particular list. So so that's why that person has given a higher self-reference rating to aeroplane, tour, country, and cycle, right? So that person is more likely to remember these words than any other words in this list. And of course that also differs from person to person. For example, if if a person is let's say that they are much more accustomed to nature, they'll be able to remember flower and carrot and violet much better than aeroplane, string, aeroplane, tour, country, and all that stuff, because they would have given a high self-reference rating for violet, flower, and carrot, because they all relate to nature. So that is what their experiment was, and their findings was also aligned to their hypothesis, which says that people who have given a higher self-reference rating to words will most likely remember those words. Or in other words, people who the words which are much more related at a personal level to people, they'll be able to remember those words much better. So so this was Rogers, Kuipers, and Kirker's experiment. And so this is actually the last topic in this unit, which is connectionist parallel distributed processing model of memory. And in textbook they've just given connectionist PDP model of memory. Okay, so this is a little bit mathematically a little bit bulky. So let me go over that. So what they're saying is that information processing takes place through larger number of simple processing elements called units, and each sending excitatory and inhibitory signals to other units. So basically what they're saying is that at a very, very deeper level in our brain, a neuron is a single processing unit, right? A neuron is a single processing unit, and that neuron basically stores some sort of information in order to recognize, in order to form a relation between other neurons and remember something. Okay, so according to their model, if you can see the image over here, this is a unit of processing, and you can say that this is a neuron. This is a unit of processing. And so basically the inputs, a flow of electric currents will flow through the neuron, and they will, as it flows, so each time a new information is given, a new set of electric currents basically flows through the neurons, right? Okay, so when a new set of electric currents flows through the neurons, based on what kind of electric currents are flowing, it will basically learn something known as weights in order to remember what kind of electric currents were passed through them, right? So for example, if let's say that these are all in neurons, let's say that these are all dendrites, and from each dendrite, from this dendrite you're getting an electric impulse, for this dendrite you're not, and so on and so forth. So if you're getting something like this, this particular neuron will learn that, okay, so in order to remember this information, we actually need to store the number of dendrites in which from which we actually received an electrical signal. So for example, if in this unit, let's say that the first neuron, the first dendrite and the last dendrite basically received the information, basically received the electrical signal. So the sum of this will be 2. So next time an electric current passes through this neuron, it won't get excited or it won't get activated unless the sum is actually lesser than greater than or equal to 2. Okay, so this is what this means is that they are very, very, very small processing unit. That's all. Okay, so in connectionist PDP model, what they're saying is that from each of these small processing units, that is a neuron, it will basically it will form connections and relations with other neurons, and basically form a model. And so each model will form relations with other models, and then they will all join together in order to form a memory. Okay.
Tarun,
So
what do
yeah,
you mean by model in a layman term?
I'll tell you about it. I'll tell you.
Okay.
I'm coming to that actually.
Okay.
So what a model or a module is basically any information that is extremely primitive. For example, let's say, for example, let's say that you are actually trying to remember a dog, right? So when you're trying to remember a dog, a model can be used to learn the color brown, and that model, and I mean, some weight, some learning has happened in the neurons, and let's say that a particular set of neurons have combined together and they form a model called brown, and that brown can actually be associated with any other stuff that we see in a real world that is actually brown. Okay, so that model is basically brown, and it can be related to any other stuff that, and let's say that another set of units, that is another set of neurons combined together to form a module called I. Okay, so that module can be actually associated with any other module, any other real-time things that we see in this world that actually represents an I. So when this I and this brown color is actually mixed up, they actually form a new meaning. So that is an I, and it is brown in color, something like that. So
you're saying using the neuron network, we are trying to create a different perspective using a unix of things which we see or which
yes,
we imagine.
yes. So basically, if one model has actually learned and it is used to represent, let's say, the color black, and the other module is basically formed to represent, let's say, a string. So when we actually combine these two modules, they can represent
But
a hat.
why would we combine them?
They will combine by themselves. That is, see, the thing is that all neurons are interconnected between each other.
Okay.
Okay, all neurons are interconnected between each other.
Let's take an example that you as a person, like, let's see the whole body, not just the brain. So you
Yeah,
saw something, or you heard, you used your auditory, kinesthetic, or visual, sensory stuff. And
right.
then what happens? Like, so you're saying that dog. Why would dog come into picture? Did we see the dog? That's why we got this color
Yes,
brown.
yes, yes, yes. The thing is
Then
that when we are actually learning, we actually saw a dog and we basically remember it as a dog. So instead of actually seeing a dog, what our sensory system is doing is that we are actually, separating the features of that dog. For example, the dog has so much hair. The dog is brown in color. The dog's eye is black. The dog has giant flaps like ears on it. So all these features at a very, very deeper level, we are storing it separately as concepts in our brain. And these concepts are actually formed using these modules.
So, just correct me if I'm wrong. So you're saying that when we see anything,
Yeah.
so we not only see it as a whole, we actually see it, we differentiate whatever we see, and we or maybe we categorize it and store it in different location of brain, like not
Yes.
location, like we can say as a metaphor, it goes to different areas, wherein whenever we need any information, let's say we saw a dog later, we saw a dog and we create whatever information we see, the color of the dog, the height of the dog, the eyes of the dog, the feet of the dog. It goes into a different parts of our brain using neuron, and later when we see, then we do relate the same thing with something else, because we just see a tree or a house nearby. This is what you're trying to say, and we connect those things.
Yeah. So see, okay, I'll give you another example. Let's say that we have a module in our, in our brain. That is, a set of neurons have actually formed a module called I, and we actually have an idea what an eye looks like. vaguely, right? And we are from seeing, like from childhood, we've been seeing, eyes everywhere. We see eyes in other human beings, we see eyes in other dogs, and everyone has pointed out to that eye, and then they're saying that this is what an eye is. Okay, so let's say that we know what an eye is, and let's say that another set of modules have actually formed, and just remember that these are all interconnected, and another set of modules have actually formed, and they represent nose, and another set of modules have actually formed, and they represent a mouth. So we actually have stored these concepts, separately in our brain through these modules. But the thing is that the moment we actually see a face, we put these modules together. These modules actually work together, they connect together, and then we will be able to associate an eye, a mouth, and a nose with a face. That's it. So even if we don't see one, for example, let's say that we are just looking at a picture of an eye. So we won't be associating that eye with a face anymore. That eye, the concept of an eye is already stored as a module in our brain.
Okay.
Okay, so the concept of an eye is already stored as a module in our brain. So we'll be able to recognize that eye as an eye itself.
Okay.
Okay, and other mouth as a mouth itself. But we are also capable of putting these together in order to say, oh, okay, this is a face. So that the face will itself become a separate module.
So are we not talking in a way that when we see something, it becomes an episodic event, and then we are trying to make meaning out of it, and then we are storing it in our maybe procedural way, that whenever we see a dog, it should come from our train of thoughts that this is how the dog looks like, or these are the colors of the dog.
Okay, no, because that why it doesn't work like that is, at a deeper level, we are looking at pattern recognition. So basically, this is really not okay. So the thing is that in episodic memory, you can always trace back to things that actually led you to remember that memory. For example, do you actually remember the first time you actually saw an eye vividly? Like or the first time you actually saw the color orange?
No.
We are not able to remember that. So if we are able to remember that, then we can trace back, oh, okay, this is where I saw an orange. I saw an orange after this. I saw another orange color after that, and I saw another color after orange after that, and that is where this is where it has led me to see this color orange that I'm seeing right now. So that is actually an episodic memory, but this doesn't actually work that way. This is basically our brain trying to intermingle some neurons together in order to form a concept called as an orange.
Okay.
Okay, so the first time you've seen an orange, it's just a concept. So you're seeing something new, and it's just a concept called orange. The second time you see an orange and someone points to it, and they say that, oh, okay, this is an orange color. So your brain has already seen this orange. It need not necessarily remember seeing it, but your brain has already seen an orange, and it has already made an association that it is called orange. It is called the color orange. So what it does is, it unconsciously trains your neurons in order to better understand the color of an orange.
Okay, I got it. I understood now. Okay, how whatever information we get, we store it in different places in the form of molecules or modules, and then we organize it whenever we need it. So we actually differentiate it in the beginning, and then integrates it whenever we need it.
Yeah.
Okay.
So this is if you see this diagram, this is how it works. If you see over here, all the modules, you can think of this as one round. That is, you can think of this one round as a neuron. You can think of this one round as a module. So because everything is interconnected, you can actually think of this as anything. It is let's say that this is a module. So this module is connected to this module, and this module is connected to this module. Let's say that you want to put this module and this module together. Let's say that this is an eye and this is a mouth. So let's say that you want to put this together, and the module that actually interconnects this will be a face.
Okay.
Okay, so that is how you will be able to interconnect this. So this concept called face is actually interconnecting these modules.
Okay.
Okay, so if all these features, basically, if all these features think of these rounds as features. If all these features represent some part of a face, this entire interconnected module is a face. Let's say that this represents an eye. Let's say that this represents a mouth. Let's say that this represents a beard. Let's say this represents a nose, something like that. So let's say all these features represent some problem, some feature regarding the face. So this entire module, this can actually form an entire module. So this entire module together is actually a face. In that, if you see, this is a separate module. 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 So in this, if you see this x1, this x1 can actually, let's say that it can represent a round black color, and this x2, this can represent a let's say the white color oval shape, and let's say this represents an eyebrow, and let's say this represents the corner of an eye or eyelashes, right? So this entire, this 1 2 3 4, x1 x2 x3 x4, this entire thing forms an eye. Okay. Right? So when we actually see an eye, these 4 neurons will get activated and we'll be able to recognize that it is an eye.
Okay.
Okay. But if we are just seeing an eyebrow, then only x2 will get activated.
Okay.
Okay. So only if all these features get activated, we'll be able to remember a face.
Saying to get the exact information, we need to look for more cues so that we can get the exact information. Like you said, if we see only eyebrow, then it's very difficult to recognize for a neuron that what exactly we are looking for. We're just looking for eyebrows. But if we look the facial expression, then neurons would be able to see that we are looking at a face, not just the eyebrows. So it's like recollecting or activating all those neurons which specify that particular thing or whatever we are trying to see. Okay.
So that is what remembering is basically. So remembering is basically, our brain activating all these neurons that basically forms that particular information.
Okay.
That's it. Okay. So so as I said, unit or modules receive information from other modules, leaves traces behind. And when I say leaves traces behind, they are basically talking about the weights that we have learned over here. So this is actually just one unit, just one neuron. So let's say that if this one neuron is actually learning the concept of an black color. So whenever we see the black color, our eye is basically generating some sort of electrical impulse. Okay, so it creates one sort of electrical impulse for black color. It creates another sort of electrical impulse for orange color. So this neuron's job is to just remember the electrical impulse that it got for black color. And that is how, and so this electrical impulse corresponding to this black color will be stored as weights. And next time it will get activated only if it gets that particular electrical impulse. This neuron. So that's what they're saying over here.
Okay.
Okay, so these traces change in strength, also called as weights of the connection between individual units in each model. Okay, so so basically, I said that our brain will be able to. This is the example that was actually given in the textbook that we have. So this is a kind of a vague example, like what they have given. So what they have given is, like, let's say that you are actually asked to recall the name of the man that you played tennis with. Okay, so basically your neurons have formed modules in order to recognize a man, in order to recognize the features of the man, and in order to generalize the features of all the men that you have played tennis with. So basically, the man that you have played tennis with yesterday is a module. The man that you have played tennis with day before yesterday is also a module. And when you're asked to recall the name of the man that you played tennis with, it is basically combining these two modules and then saying, oh, okay, I play tennis with 2 people. Now what? Right? So I play tennis with 2 people. Which one are you asking about? Right? So if there is only one man that you play tennis with, the module corresponding to that man is activated. If there are multiple men, then you play tennis with, then the information required on the man to activate more modules. That is, you need to basically say, okay, what is the color, skin color of that man? What is the height of that man? What is the body build of that man? Each of these features are actually stored as separate modules in this connectionist PDP model. So if you actually need to pinpoint to that particular, feature in order to recognize the exact, person that you have to select, that is, recall the name of the man that you played tennis with. So what our brain implicitly does is that when you actually hear a sentence called recall the name of the man that you played tennis with, it basically just inhibits, that is, it basically just discards all the information that you have of the women that you play tennis with. Because it is man, you are not even considering the modules that involve women in it. Okay, so that is what this connectionist PDP model is. So this is actually a kind of example that we have. So at very, very, very deeper level, this is how our neurons will actually store information. So this is basically this is what we see right now. Okay, so our immediate larger modules that actually knows the concept of 8 will actually look like this. So basically 8 is not just a picture that we are seeing. 8 is a concept. Okay, 8 has a curve like this, 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 something like that. So 8 is a concept that we are seeing. So in order to generalize this concept, the more 8s that we have seen, the more generalized the concept will be in our neurons. Okay, and let's if you look at this layer, convolution layer 2, you can see the curves that are being stored in a particular module. Think of each of these boxes as a particular module. Okay, so in this module, this curve is stored. 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 This curve, this curve. So in each of these modules, a particular curve is stored to remember the concept of an 8 rather than just the image of an 8. So if you actually see some other 8 also, some other kind of 8 also, you'll be able to activate these modules in order to say that, oh, okay, we are seeing at 8 right now. Something like that. Okay, so this is with 8. And if you see, let's say that this is a car that we are seeing. And we have actually, from the childhood, we have actually stored the generalized information of a car. Okay, so you can actually understand each of these as a neuron. In the first set of images, we can actually consider each of these blocks as neurons. Okay, so this neuron is actually storing this particular edge. That is a black and white, and that's a black and white edge that is oriented at a particular angle. Let's say that this neuron is showing a black and white edge oriented at another angle. So we have all these neurons which have a black and white edge oriented, at some angles, and our brain, and this actually forms a module to form something like this. If you see, this is basically a window, and this is basically the bonnet and all that stuff. Okay, so these edges basically form the modules to become the edge of, let's say, this edge of a car, and another set of edges basically forms a module to say become this edge of the car. So all these edges again will form a module in order to recognize this car, and that is what this is. Okay, so does anyone have any doubt on it? I know it's a little bit complex concept. So if anyone has any doubt or anyone has any insights towards it, please let me know.
I see your thank you. Next slide is thank you slide. No, so probably I will take some time to probably give an example.
Pardon me?
Shall I try to give an example?
Yeah, sure.
Okay. Pratika, we all play drums, right? So you had to act and you had to let your team decide what your telling. So you will try something, nobody might catch it. You'll try something else, nobody might catch that. So you keep different things so that you can activate certain memory in the audience, right? So how we do that? We do that because we know
You
that.
are talking too technical, Prahad.
No,
I was
no.
thinking only Tarun is talking that way.
Okay, I'll go slow.
Thoda easy karo question ko.
Okay,
I couldn't understand.
the model is about how we are storing something in our brain.
Yeah.
That we are all clear on, right?
Yeah.
Now, when any concept, let that be a ladder or a mango or whatever, we don't really take a Xerox of the mango and put it in the brain, right? Brain
Yeah.
is storing it some other way. How
Okay.
does it do that? So if it's a dog, for example, it has all these attributes. It has a sound, it has a look, it has a length, breadth. So brain catches all this with our eyes. We might be feeling it, our touch. All the five senses we have will be catching that.
Yeah.
All this goes inside and brain gets all these impulses. It will save it not as what we see or what we hear. It actually breaks it down to the very minute small points that it can break down it down to. And all those small pieces of a dog might have, let's say, a few percentage common with similar breakdown of a mango. For example, a color, or for example, a shape of an eye. A shape, little circle, might be common for eye of a dog and a mango. So when you break things so small, all the information you can think about a dog, break it down to very small pieces. All the information you can think of about an elephant, break it down to smaller pieces. There'll be some commonalities, right? Some of those will be common. Correct? Agree?
Yeah.
At least they have both some legs, some tail,
Yeah.
etc.
Yeah.
Okay, some small pieces. When you break it smaller and smaller pieces, commonalities will be more. So the elephant and concept of elephant and concept of dog goes into a brain as a network of all these small chotu pieces together.
Yeah.
Okay. Now again, this network is not only for brain. A part of it is a part of some other memory also. For example, cat, as we said. So when you see a elephant next time, all these together fires and bang, that's your thought of an elephant. When a cat comes, a few of this and a set of other things fire, and that is again cat. Now, these work in using the activation as well as inhibition, those two things. So some triggering happens using activation. So I know that this is that, we activate that. I know that this is not it, so we inhibit it. Using these two mechanisms, certain neurons will fire, and the collection of all that firing will be the concept as we store in our brain.
Yep.
Little more complex, na? I don't know how to make it
And those things which you were saying, na, chota, that is all actually called dendrites. So whenever we try to learn new things or we see something for the first time, we actually grow dendrites, and that dendrite becomes stronger and converts it into a memory.
Awesome. How do you spell that?
DNDRIT.
DENDRITES.
Dendrite.
So
Okay,
you
nice
see
to
this,
know.
those are very delicate part which actually grows when we
Dendrite.
try to learn something new. So even in the learning thing, we learned that we learn whether it's consciously or unconsciously, but whatever we repeat becomes our memory. So whenever we learn consciously or unconsciously, we grow dendrites, but we don't remember everything because those dendrites dies eventually.
A question, and this is a physical thing like a muscle or something.
Yes.
Oh,
Yes,
okay.
it's
I
a
thought
physical
it's a
thing.
electrical. I thought
It's
it's
a
a
cell. It's a
It's a
cell that
cell.
forms
Yes.
in our body. So
Yeah.
this is basically the neuron, and these are the dendrites, and these are the
Yeah.
axons, right? So this
So
is how
dendrites
electrical
become
impulses
neuron,
are
right?
carried out.
Tarun,
Yeah.
dendrites become neurons, right? Once it's stronger enough.
Yeah.
Okay.
Oh, that's
Right.
nice to
See,
know.
this is actually a dendrite. This is actually a dendrite. Okay. So this is actually a dendrite, and this entire thing is a neuron. And it basically conducts electricity, like this. So basically this axon and the entire neuron is basically storing the information as a weight.
Okay.
And these electrical impulses come through these synaptic terminals like this over here. This is called a synaptic terminal, and it comes from another neuron to this neuron via this.
Okay.
Okay. So these actually form a network of neurons.
Yeah, because here when we are talking about memory learning, it's important that we should go through a little bit about brain science. Because when we will study brain science, then all these things will make more sense what Tarun is talking about right now. How it converts, how modules convert into molecules, how it one small unit become one neuron. This is through dendrites, and then the whole learning, whole memory process help us to understand things the way we understand in general. The more we grow up, the more we understand things.
I actually thought of first explaining what a neuron is and how it conducts electricity, but I didn't actually think, it is actually not even given in this much detail in our textbook.
Yeah,
So
yeah, it's not there because
that
I
is why I
studied
didn't
in
actually go to that.
yeah.
Do we have this in our syllabus?
Yeah, it is called PDP model. Connection
Okay.
is PDP model.
I mean,
It's not given us too much this thing, huh?
the dendrite and the rest of the neuron
Yeah,
stuff.
he mentioned that in between. I heard that
Yes.
Tarun mentioned dendrites in between, and dendrite is the start point. Like even we studied that Prahash even during our learning model,
Okay.
how learning happens.
Okay.
Okay, the learning happens when we learn consciously, unconsciously. We grow dendrites, but we convert into memory only when we repeat those
You
whatever
took that
we
class.
are watching. Huh?
You took that class.
Yes.
Oh, my dendrites for that class did not grow much.
That's okay. That's not my problem. I learned it very well. So the idea is I should understand the concept and I should teach the concept. And the thing is,
Okay.
dendrite and this neuroscience, I'm studying it for 3 years. So I understand a little bit already. For the
Okay.
first time, it went out of my head. So it took me time to understand what actually is happening. So
Okay.
don't
No.
worry, you will get through.
Thank you. Thank you. Okay.
Kritika, I have posted in the chat. Just check.
What?
It's from
About
my
Dendrite.
notes. Okay.
I'll read it. Dendrite. They are like tree branches at one end of the neuron. The dendrites receive messages which is passed on through the axon. At the time of birth, there are very less dendrite as the experience is also less for the child. As they grow and gather the knowledge through experiences,
Yeah, that's
through
true.
their movements, these dendrites become more and more and creates webbing effect.
Yeah,
More,
because dendrite can grow only when you have learning abilities. So once a child started learning, he or she
okay.
started growing brain muscle. So how will you grow brain muscle? Through dendrites. So the more
Okay.
the dendrite is, the more the understanding a child get, and slowly, steadily, it becomes like a very complex, uh, what do you call the complex structure of the brain, which we have as an adult because we have much better understanding than the child or even the adolescent, and the people who are older than us must be having better understanding than we have. So it's
Okay.
all about what, and again, what kind of dendrites we grow. That is also important. That again come into mindset. What are we feeding our brain? What we are
Okay.
learning? Are we learning positive things in life or negative things in life? If we are growing, if we are studying or learning positive, then it will take us to a very different level in life. If it's negative, then it will always keep us unhappy and sad about so many things. So again, what priorities do we give in our learning process also decide the course of our life.
Okay. I'll take 2 more minutes to just to present another little tricky concept. Again, I'm not an expert in this, so I must be making some stupid mistakes. Please
But it's not stupid.
start.
It's
So
good. We
this
are
is
just
about
studying.
this is about face recognition. So how
Okay.
do computers do face recognition? There are thousands of faces. They cannot do a pixel to pixel match. That'd be a lot of work to do. So as and
Okay.
when they receive a particular person's image, face image, they also store something called metadata for the image. So the person's face, imagine 1 million faces, and
Mhm.
computers have to comes 1 millionth and one's next image. We have to see who out of this 1 million is this person. How? It's very difficult to go compare one to one, what they do is for every image they take, let's say color tone, then eye style, then the ratio of eye to nose, then the ratio of nose tip to mouth. So they have many parameters like that. That's called metadata. They extract metadata for each of the images and store it separately. And then before comparing, they reduce the number of possible candidates by comparing this data. So for example, square face, circle face, oval face. Now you can immediately go, if the newcomer face is a square face, you can eliminate all the other circle faces immediately. So that is the elimination process. Probably Tarun was talking previously. If there is a tennis player was a man, then you can reject all the women's, similar to that. Then comes, okay, if the big eyes or small eyes or eye to nose ratio this much, again you can eliminate a lot. So some of these properties for the newcomer model, that new image, its metadata will be reinforcing your search. So you will filter your search to that extent. Then within that, some of the other metadata will eliminate a few of them more. So that's how you very fast you go down from 1 million to, let's say, 5 images. Then you do more comparisons. So,
very technical but interesting.
yeah, so that's again one good advantage of splitting the information into small processable chunks instead of keeping it as a big chunk.
Yeah, so the computer is doing the same thing what we do it in our brain.
Yeah, so that's what I was coming to say.
It's
So yeah, so all this exactly does what are the current artificial intelligence that we have in computer science is exactly taken from how our brain processes information, and that is this connectionist PDP model. I mean this this image that I have used over here, this image and this image are all actually taken from computer science concepts. They are not, I mean, they are not actually given in any neuroscience concepts. They are taken from computer science concept because they are using the exact same, method to do it. Even this video that I'm about to show you right now, I wanted to show this video. This is also taken by artificial intelligence of how to actually recognize an image. And they have taken all this research from neural science, how our brain processes and stores data. So I'll just show this video. You will get a better understanding how PDP works. Can everyone see this video? Hello?
Yeah.
Yes, please. Yes, please.
Yes, it's coming up.
By the way, there is no audio. So it is basically trying to generalize the concept of an A. So the more A it gets, the more it will generalize that concept. Okay, so this A got generalized to this was generalized to this. So these are all the small pieces that this thing is learning. So this is a module. This is a module. These two combine to become this module, and these combine to become this module, and these combine to become this module. So these are all actually concepts that form A, and this concept can also be reused for some other letter. So basically, let's say if you see over here, it tried to match this base concept to E, and it matches a little bit. That is 2%. Try to match it to D 1%, but it matches a lot with A, and that is why it is an A. But if you actually take only this part of it, just this, let's say the first nine blocks of it, then it will have more correspondence with the letter E and more correspondence with the letter A, because it is a concept that we are using to generalize things. So here, this is basically suits more with the concept A, and that is why it has 92% accuracy.
So this PDP model is more like every smaller thing has much more smaller than that, which are modules, and the greater ones are concepts.
Yes.
That's right.
Yes.
Okay.
Actually, this theory is an abstract theory, but it touches the real life activities. It's very difficult to explain it, but it just happens. And that happens like even in nanoseconds. You know, it's quite interesting.
I mean, the recognition happens in nanoseconds, but learning happens
Yeah.
over a lifetime.
Yeah, obviously. The way we grow our dendrites like a baby plant, the baby will get good fruits of dendrites.
Yeah.
Good decision making, kind of. All right, I think that was.
Yeah. So that is it.
Yeah, Terry,
Okay.
thanks a lot
So
for
what we covered in this unit, we studied the Vog and Norman's model of primary and secondary memory, which is one of the question for our what is that, the assignment as well, right? Or the second one.
Yes,
Yeah,
yes,
it's
it's
Vog and
more
Norman.
normal.
One. And then we studied the Atkinson and Schifrin's stage model.
Yeah.
We studied the level of recall, level of processing by Crack and Lockhart. And today we studied self-reference effect and that what was that? PDP model?
Yeah, Craig
That's
and
it.
PDP
Turing.
model. Yeah.
Oh, that's
Connectionist PDP model.
okay. All right. All right. Anyone has any question for Tarun? I'm gonna stop the recording.